Okay, so we are in section 7.6 here, and we're looking at systems of linear differential equations again. Sorry, my printer kind of smudged that a little bit. So this section is pretty short in your textbook, and it's actually even shorter when you look at what we're going to be going over. Basically, the idea here is that we're revisiting the concept of systems of linear differential equations, which we've already dealt with. We've talked about how to solve these things using elimination before. They're the same types of linear systems as before, but this time we're going to take a different approach and use Laplace transforms to try and solve them. The book, if you read through this section, focuses on some applications. So it looks at like spring mass systems and electrical networks and things like that. We're not going to be looking at those applications here. We're really just looking at solving the systems as they are. So this will be a short section. We just have two examples of linear systems that we want to solve before we move on to chapter 8, where we attack the subject of solving linear systems in a much more general sense. So to start with, we have this system of equations below. dx dt equals 2y plus e to the t. dy dt equals 8t minus t. And then we have these initial conditions where x of 0 and y of 0 both equal 1. So for this, I want to start by rewriting my system where I collect any of my x's and y's along with their derivatives on one side of the equation, and anything that's just a function of t goes to the other side. So this is going to look like this. I'm going to call it my dx dt. I'm just going to call it x prime minus 2y equals e to the t. So I subtracted that 2y over. And then over here, I'm going to subtract the 8x over. So let's call that negative 8x plus y prime equals negative t. Okay? So, and I'm intentionally lining up x's and x primes, y's and y primes for organizational purposes. Now what I'm going to do is take a Laplace transform of both sides in each of my equations here. So if I take a Laplace transform of this side, the Laplace transform of x prime, actually let me just go ahead and write that. Laplace transform of x prime minus 2 times the Laplace transform of y will equal the Laplace transform of e to the t. And over here, negative 8 times, I should be using my curly brackets here instead of parentheses. Got to be consistent. Negative 8 transform of x plus transform of y equals my transform of negative t. Okay, so let's bring this down here. We can evaluate all of these directly. So for x prime, because I have two functions of t here, x and y, when I take my Laplace transforms, I'm going to denote those by a capital X and a capital Y respectively. So this guy right here becomes s x of s, notice it's a capital X, minus x of 0 minus 2 times the transform of y, which would look like minus 2 capital Y of s, equals, and then I need my transform for e to the t, which is 1 over s minus 1. Okay, then down here, negative 8 times my Laplace transform of x, so that would just look like minus 8x of s, plus the Laplace transform of, this was a y prime there, y prime, which would be plus s y of s minus y of 0. And that will be equal to the Laplace transform of negative t. I can actually bring that negative out. Laplace transform of t would be 1 over s squared, so this becomes negative 1 over s squared. Okay, now x of 0 and y of 0 are both equal to 1. So I'm going to say 1, 1. And I'm going to plug a 1 in for each of those and then add that 1 over. So this tells me that I have the following. S times x of s minus 2 times y of s equals, I'm adding a 1 over, so 1 plus 1 over s minus 1. And then down here, adding a 1 over, I'll get negative 8 x of s plus s y of s equals 1 minus 1 over s squared. Okay, now from here it's going to look basically like elimination. I'm going to start by trying to eliminate the x from the system. So I'm going to look at what I have. I have s in front of this x and negative 8 in front of that. So I'm going to multiply my top equation by 8 and my bottom equation by s, and then adding those results will eliminate the x from this equation. What does that leave me with up here, though? I'm going to have 8 times negative 2, which is negative 16, y of s, s times s, y of s, so I get plus s squared y of s equals, multiplying this side by 8, I'm going to have 8 plus 8 over s minus 1. Multiplying this side by s, I'm going to get plus s minus 1 over s. Okay? And now I'm going to work on simplifying things down a bit. So over here, if I were to factor the y of s out, I'm going to have y of s y of s times s squared minus 16, which is the same thing as s plus 4, s minus 4. So that would factor even further. And then over here, I'm going to have the same thing that I had before. 8 plus 8 over s minus 1 plus s minus 1 over s. Okay? Solving for y of s. I'm going to give myself a little bit more space here. Y of s is equal to 8 over, I'm dividing everything by my s plus 4, s minus 4 now. S plus 4, s minus 4, plus 8 over, I have s minus 1 there, s plus 4, s minus 4, and then I have s here, so plus s over s plus 4, s minus 4, and then minus 1 over s times s plus 4, s minus 4. Okay? It's fairly cluttered, but what I want to do is combine all of these into a single rational expression. So I'm going to end up with this, y of s equals. I'll let you do the work of getting the common denominator here. It's very simple to do, just a little bit of algebra. But what the numerator will look like once everything has been simplified down is this. S cubed plus 7s squared minus s plus 1 over that common denominator, which would look like s times s minus 1 times s plus 4 times s minus 4. Okay? Now, we've dealt with this kind of thing before. What we want to do now is expand this thing using partial fractions. And what I'm going to do is this. Partial fractions. Again, kind of like we've been doing recently, we're kind of skipping the work of partial fractions just because we've done several examples where we have shown that work. And at this point, it's just kind of needlessly time-consuming. So you do the work and make sure that your result is coming out the same as mine. But what this should come out to is 1/16 over s minus 8/15 over s minus 1 minus 53 over 160 over s plus 4 plus 173/96 s minus 4. Okay? From here, we could do a very straightforward inverse Laplace transform of both sides to get this. Y equals 1/16. And then the rest of these are exponential functions when we take their inverse transforms. So I'm going to get 8/15 e to the t here minus 53 160ths e to the negative 4t from that denominator there plus 173/96 e to the 4t. So that's part of our solution. We have y solved for now. Obviously, we also need to solve for x, being that this is a system of equations. So looking to x next, what I can do, instead of going through the elimination again, which may be important to do that. We may need to do the elimination again, eliminate the other variable. In fact, in the second example that we're going to do, that's going to be better approach. But in our case, we can actually use substitution. So if you notice, I'm solving for x, and I have an equation in my original system where x appears explicitly, not its derivative, but x by itself. Not only that, I've solved for y as a function of t, so I can find y prime, plug it in here, and then just isolate the x in that equation to solve. That's what I'm going to do. But first thing I'm going to do before that is solve this guy for 8x. So I'm going to say that 8x would equal y prime plus that t right there. 8x equals y prime plus t. That's from our second equation in our system. So that means I need y prime. Y prime can be found directly just from what we have here. So this will be negative 8/15 e to the t plus the derivative of this guy is going to be 53 over 40 e to the negative 4t, and then this one right here is going to give me plus 173 over 24 e to the 4t. So finding that derivative is straightforward. Now I can use it as a substitution right here. So this would tell me that 8x is equal to that derivative, negative 8 over 15 e to the t plus 53 over 40 e to the negative 4t plus 173 over 24 e to the 4t. And that's my y prime, but then I have a plus t showing up in there as well. Okay, now we just divide everything by 8 and call it a day. X is equal to negative 1/15 e to the t plus 53 over, this would be 320 e to the negative 4t. Divide this guy by 8, and we're going to have plus 173 over 192 e to the 4t, and then finally dividing that by 8 will give me 1/8 t. Okay, and that gives me x. All right, so again, the idea was we had the system, and we took Laplace transforms of both sides of the equations in each equation, and then that gave us this capital X and capital Y, those Laplace transforms that naturally would have occurred there. We solved that system using elimination, and then we end up with just one of those, either capital X or capital Y. Solve that with an inverse Laplace transform like we've been doing in this chapter to get a solution for whichever one we isolated, y in this case. And then in this example, it was helpful to differentiate that, find an equation where my other unknown was given explicitly, and substitute dy dt in there and solve for x algebraically. So that was a great way to get our solution. In the next video, we'll do another example, which will involve second order equations, and it's kind of the same process. So we'll take a look at that in part 2.